is my pleasure to introduce our two next speakers, John Levy and Katie Porsche at SEEQ in New York, UK, and Italy. John Levy is the CEO, chair, and co-founder of SEEQ. SEEQ is a scalable, energy-efficient quantum computing company. John has a different background than many speakers before. Namely, he was a founding partner of L Capital Partners, a $185 million seed stage venture capital fund. There he led investments in the technology sector. Prior to that, to his work in the venture capital, he worked at Interval Research Corporation, Palo Alto based, and there he spun out and was a CEO of ePlanet, a pioneering computer vision company funded by Intel. So very exciting background, and everyone also feel free to ask questions about this part that is also important in the quantum computing domain. And then we have Katie. Katie has been a quantum engineer at SEEQ the past 3 years. She's working on developing SEEQ's control firmware for automated qubit calibration and validation. Before joining SEEQ, she was a postdoc at UCL, University College London, working on C-shunted flux qubits, and has a PhD from Royal Holloway, London, and developed novel amplifiers for qubit readout there. We will start with a keynote by John, then do a Q&A, then have a really exciting virtual lab tour and do more Q&A.
Okay.
John, please
well,
take
thank you.
the keynote.
It's a great introduction, and it's funny because you use the word background. And first off, thank you for inviting us to participate. We've been very excited and done a lot of preparation for this day. And it's great that Katie can be involved, and we have others in the background who've been helpful as well. You mentioned my background, and one of the things that you mentioned was helping to start a company which was really one of the first computer vision companies back in the mid-90s. And the very virtual backgrounds that maybe you are using or I'm using today, we invented in 1995. And it's interesting that when I get together with one of my other industry colleagues, Hartmut Neven, who runs the quantum computing program at Google, he also has a background in computer vision. So it only shows that people are able to kind of pivot from the kind of technical domains that they're working in, from doing, kind of one interesting area to another. And I think there's no better area, as Danny Holmes was saying, than being involved in quantum. So what I wanted to talk about today, and this is going to be a higher level talk initially, and then we can go, kind of as deep as you want. And you'll see some things in our video, is to talk a little bit about quantum in the context of energy, climate, scalability, and doing so in a very practical way, because we are a commercial company. We spun out of a company called Hypris, which, for those of you who may know, is one of the world's leaders in superconducting electronics, and particularly it was operating in the RF domain. And Hypris's roots go all the way back to the founding of IBM's superconducting electronics division, which is why we're based in Westchester County, not far from Yorktown Heights. So our original idea around starting SEEQ was not only to be able to work in the commercial domain and in quantum and in high-speed computing, but we were very interested from the start in trying to build energy-efficient quantum computers. Because what we've seen in classical computing is that we are building these fantastic data centers around the world that are scaling, enormous requirements for computation. And we're looking at things like, recently it was crypto and now it's AI, but they're using a larger and larger percentage of energy to run them. And we felt from the start that we needed to take on an energy efficient way of thinking in terms of our designs, and also around scalability. So I wanted just to include a couple of slides that I typically put in there. This audience obviously knows all of these things, because I was last week briefing the senior management team of LG from Korea. LG is an investor in SEEQ, and we were talking about batteries. And one of the things that is something that we should not overlook is that companies that are making, this company, LG, is a world leader in batteries for for like EV applications and other things. And yet they still are using, if you will, digital tools to model quantum mechanical things, which is, if we think about cathodes or anodes or complex chemistry involved in batteries, they're still thinking in a digital fashion. And what we're trying to do is not only to build these sort of systems, but educate companies so that they understand that the very things they're making are fundamentally quantum mechanical, and that therefore we need, again, as Danny mentioned at the end of her talk, in terms of applications, we need to be able to apply quantum systems, quantum simulation in this case, to help model next generation molecules. So this is what I included to them. But look, the applications that we're focused on, or our customers are focused on, I should say, are some of the ones that others have mentioned in their talks. Clearly, battery technology is really, really important. And from that perspective, we're working with companies like Merck and BASF, where BASF is the largest chemical company in the world, and 15% of their volume that they do is based on one particular catalysis process, where they have tasked us with trying to build a quantum simulation tool that they can use for this process, because they want to remove the energy content, which is really, really significant. We're doing a similar thing with Merck. But we can see other applications like power grid optimization, carbon capture, all of which have the potential with scaled quantum computers to be able to tackle them. In fact, we're in conversation with the team from LEAP, L-E-A-P, at Columbia University, that has a $35 million National Science Foundation grant to build a next generation climate model, and they want to incorporate quantum computers into it. They haven't done it before. And they said one of their biggest challenges is they don't have a method by which they can model a cloud, a simple cloud. And you think that this would be something that would be straightforward. It's not. It's a really complex problem, and one that probably quantum computers are best at resolving. So these are the kinds of very practical sorts of problems that people are looking at around climate change and around energy. So if we go back to a little bit and think about some of the work that the pioneering work in quantum, one of the most important ones was the announcement that Google achieved so-called quantum supremacy in 2019. And that made the front page of the New York Times and periodicals around the world. But it was a study that came out, and by the way, they were partnered with NASA when they did it. But it was a study a year later that when NASA put out a new paper that looked at the quantum supremacy experiment from a different perspective. And they were looking at it from the point of view of energy. And they were looking at trying to compare running random circuits on classical supercomputers. They have one called the Electra. At the time, Summit was the most powerful supercomputer in the world, and comparing it to the performance of Google's QPU. And you'll see that the energy cost was a tiny fraction, if you will, orders of magnitude lower power for running the equivalent circuit complexity with an equivalent target fidelity. And so what we can think about there is that quantum computers have the capability not only of doing things which are kind of NP hard and intractable in the classical realm, but we can even think about them as running, if we can figure out how to scale them, to run all kinds of other classical circuits that we can imagine at a much more energy, or less intensive basis. So So in fact, today, if you look at data centers, I mean, really data centers, and these are hyperscale data centers that are built by companies like Microsoft and Google and Amazon, et cetera, Facebook, et cetera, are all built around the constraints of energy. And so in solving the energy issue, it unlocks our ability to be able to build much, much more scalable data centers. So then the question is, how are we going to scale them? And so again, what we've looked at are three different areas that we think are important. The first one is to build quantum systems on a chip. And I'm going to talk about the rationale for that, but it's a really important one. And it's what you're going to hear probably most about. The second is being able to look at quantum computers as part of a heterogeneous data center, where we're connecting quantum plus GPUs plus CPUs. And this is a different kind of, I want to make a difference between heterogeneous computing and multimodal quantum computing. Danny, at the end of her talk, I think somebody asked the question around the idea of combining different qubit modalities or technologies within the same quantum computer. And I think that's exactly what we're going to see. In fact, going back to computer vision, what made computer vision work for us was that we discovered the way we could combine different technologies to do different things yielded a much better overall technology and better probabilistic return. And so we can think about multimodal quantum computers, but as we think about solving for things like quantum system calibration, for running quantum classical algorithms and support of doing error correction, we can imagine a world in which we integrate GPUs and CPUs with quantum computers. And then the third area is going to be application software. So let me go into talking about the first one, which is essentially to build an integrated quantum system on a chip. So if we go back and look again from a historical perspective at the development of classical computers, what we see is you have an example of one of the very first ones, the ENIAC in the UK, I guess you'd say the Hercules. And these were computers that were built at the tail end of World War II. They were digital computers, truly digital computers, but they were based on vacuum tubes and connectivity that looks like a telephone switchboard. And so the idea was there were people who had the idea to try to scale these up. But as we know, they were very error prone, very expensive, very difficult to operate. And it came just a year later at Bell Labs was the development of the first transistor, the first solid state device as a switch. And then we saw the integrated circuit from Fairchild, Intel's first microprocessor leading up to, for example, today, NVIDIA's Grace Hopper superchip, which is powering the most advanced AI applications in the world. So the point is that we didn't end up scaling up these early prototypes of classical computers. We actually ended up scaling up solid state and integrated electronics that enable us to get to the kind of massive integration that we've seen today. However, if we look at what some companies are using, I'm just using this as an example because it's publicly available. This is IBM showing their roadmap for a 2033 quantum computer. And what you'll see is on the left, a qubit module, and these are superconducting qubits, that have a passive wiring from their chips where all of the essential aspects of a quantum computer. So think about control, readout, reset, multiplexing, error correction, et cetera, are all done essentially at room temperature, maybe some at cryo-CMOS, but typically at room temperature. And you have enormous connectivity problems. You've got lots and lots of cables. You have signals that are going from analog to digital back to analog. You're going from cold, let's call it 20 millikelvin, up to room temperature and back. So you have system latency. And you're using microwaves to control them, which are inherently energetic and need to be have the heat dissipated. So the more you scale, the more heat you're injecting into the cryostat, which both at the chip level and at the cable level at all temperatures. So you have to address all of that. Again, we don't think that is terribly scalable. And so our notion is something like this. And by the way, just to give you, I'm going to give you some numbers about this. This is an example, I should say, of Righetti's 4,000 qubit quantum computer. This is just the cryostat aspect of that. There are no room temperature electronics, no connectivity, et cetera, just the dilution refrigerator. And so what we looked at was to try to develop an energy and a cost budget for building such a system. And you can see that it takes about 167 kilowatts of power, and it's going to cost somewhere north of 34 million. We've been told it's more like 40 to 50 million dollars to build. And so if you end up wanting to scale that up, you'd end up with, let's just say, 1 million qubit system, and being very generous on the assumptions around multiplexing and cost reduction for electronics, you end up with systems that cost something like $700 million and use 13 megawatts of power. This is the kind of power you would need in a small nuclear power station. So this is obviously not, what we want to scale. And these are, for anybody who cares, this is how we calculated the numbers. We're always open to having people look at these and challenging them and updating them. And, the DOE has been working on this exact work because they want to understand this, the Department of Energy in the US. But you can see this is where we get 13 megawatts of power. So if we think about the development of quantum computers now, let's apply that. Let's just say that we think one of the most advanced computers in the world on a commercial basis is the Sycamore 2 from Google. And you can see that it's running with lots of room temperature electronics, lots of connectivity of cables, of coax cables, et cetera. You'll even see in their DR all of the connectivity that's there, just to actually have a very small module of qubits that you can address. And we also see that that there are different qubit modalities. So we know, photonics and ion traps, and obviously superconducting qubits and silicon dots, and et cetera. And so what we've said is all of those quantum modalities, all those technologies need readout, control, fast reset, better connectivity, multiplexing, error correction. And to do that, we've said at SEEQ, let's see if we can build a chip that actually does that and in whole or in part supports all quantum technologies. And that's what we're doing. And then we can scale that up for whatever you need. So what we've done, and this is coming out, some of you may know that we released our first quantum computer last summer called SEEQ System Red. We built it as a reference system to be able to run full stack applications over the cloud, universal quantum computing, 2 qubit gates. I think our gate speed was, Katie, I think we were at 39 nanoseconds. And, we had about 98.6% 2 qubit gate fidelity, et cetera. And so we've been able to run some things. There's going to be a press release coming out next week about some work that we've been doing with a company called HQS, letting the cat out of the bag. But what we have done is to build a multi-chip module architecture where our chips are running not on CMOS, but we're running on single flux quantum. So these are SFQ chips, not CMOS chips. So we're not using transistors, we're using just some junctions, and we're using them at 20 millikelvin, and where we actually put chips on top of chips, just as you see in the picture here. And by doing that, we have connectivity via capacitance. And our connectivity, again, this is operating at 20 millikelvin. So this is much, much colder than one can do at cryo-CMOS. And just to be clear, cryo-CMOS can work. The problem is, from our perspective, it's too slow. It's too, so our chips operate at 10 to 40 gigahertz. Whereas when you crank up the power in a cryo-CMOS chip, of course, the more power you put in, the more heat you're creating, which means you have to dissipate it. They're also too noisy, so they're too noisy, and they use too much energy, as I've mentioned. So our chips operate at 3 to 5 orders of magnitude lower power than CMOS, and therefore a lot less heat dissipation. And our chips are also operating in a fully digital fashion. And what that means is we can take advantages of things like digital multiplexing. So we have not announced it yet, but we will at some point. Our ability to multiplex our circuits, meaning that we can put multiple signals in a single cable. So theoretically, in CMOS, you can do that with an RF signal that needs to be calibrated, and it's very hard to do. And you can maybe do 4 signals in one cable. With digital multiplexing, you can do, in theory, up to 64 signals in a single cable. So by also doing this, we're not using microwaves to control our qubits and to read out our qubits. We're using single flux quantum pulses and flux bias in order to control our pulses. And again, these are all digital functions. So it helps us to maintain better system stability, et cetera. And then, of course, by doing this on chip, the cost of doing this goes way down, the speed goes down, and most importantly, and this is really for error correction, for readout and for error correction, because we're not doing all these round trips that inject a lot of system latency, and we have chip-to-chip connectivity, we have latencies that are, measured in picoseconds and in small numbers of nanoseconds. So we have extraordinary connectivity, which gives us the time to be able to do error correction. And so we're not doing it yet, but we will be. And so we're building an architecture that supports at least local on-chip error correction. So in order to do that, we can put all of these functions, as I say, into a chip. You're going to hear more about that in a bit, but it also, we believe, enables us to get to a much better scaling, because we no longer have to address things like, in a very practical sense, the number of coax cables you would need to control and read out a qubit. Today systems use anywhere between 1 and 4, typically 2 or 3, and depends on whether they're using tunable couplers. But the point here is that we reduce that down to a very small minimum. And so our system, compared to the system you saw before, if we use this on a chip basis, doesn't require a nuclear power plant. It's not 13 or 14 megawatts, it's 63 kilowatts. So here we have a solution that addresses energy efficiency, addresses scale, addresses cost, addresses latency. And I think the point of all of this when thinking about scaling is that you need to solve for all of these things. You can't simply solve for one of them in order to build a truly scalable system. So this is a rendering of what this kind of system would look like. And this would be for a very large number of qubits. So what we think about then is, how does that then kind of disperse out into the quantum community? And so we've given examples of companies that have different approaches, and you'll see that I mentioned this approach, this chip-based approach, works wholly or in part depending on the quantum technology. And so for superconducting, which is where we're initially focusing, we are applicable to all the quantum computers coming from IBM and Google and from Amazon, Rigetti, IQM, and others that are working in those domains. And as we think about silicon spin or silicon dots, we can also think that with some other supporting technology, so it requires some additional engineering, we're relevant to readout, reset, and error correction. But what's interesting about this chart is that it shows for all quantum modalities, we are relevant to readout, error pre-decoding, and potentially error correction. And so the examples that we've cited with IonQ, PsiQuantum, and Pascal are simply the kinds of technologies they represent. There are other companies, obviously, that are doing this kind of work. So we talked briefly about this idea about what we're doing on a chip basis, but now let's talk about heterogeneous computing. So today, what we can see, this is, I would argue from a commercial perspective, probably the most interesting and important set of technologies for building classical data centers, and it's coming from NVIDIA. So this is the new Grace Hopper superchip that's going to be incorporated into their reference design that gets then incorporated into the data centers. And what we think is that we're going to see the same thing happening in the quantum domain, but they're going to meet. They're going to become combined, where we're going to see a quantum enhanced data center or a GPU enhanced data center with quantum, depends on how you want to look at it, in support of each other, again, to run quantum classical algorithms, which we see from an industry perspective is exactly what's required to support error correction and support system calibration. And then the third part of this is using application software to be able to do it. Katie's been working a lot in this area around automated bring up, for example, of 1 and 2 qubit gates, and doing it in a SEEQ SFQ and cryo-CMOS way. But if we think about going back here and we think about what NVIDIA does with CUDA, CUDA is a set of requirements from a firmware perspective, but then tuning some of the capabilities of their chip to support core algorithms in verticals. So we can think about energy, we can think about AI, we can think about and machine learning. We can think about quantum simulation, et cetera, and building out these areas that emphasize these in the stack. So, I come back to this idea of, at the end of the day, it's about the supporting the applications. This is really what's I think the most important part. And then lastly, one of the things that I wanted just to mention is, from an entrepreneurship basis, how do you think about a business model when you're developing this? And so one of the ways that we look at it is to try to understand what value we're bringing. And if you think about it, it's a little bit like, if you think about classical computing, and imagine you have an array of transistors. That array of transistors can be put together at a higher level through an ALU, through an arithmetic logic unit, to perform, basic math skills, right? And transactions. And then if you think about it, you can then put in memory, and it can be cache memory or L1 or L2 memory on board. You can have connectivity, you can have power management. There are a number of different functions. And as we increase those functions within what will become a microprocessor, the value of what you're able to do increases. So today, if we simply have a module of qubits, that doesn't do much for us unless we have a whole rack and racks of electronics that run, control, readout, multiplexing, reset, in the future, error correction, et cetera. But if you can imagine that by doing this massive integration on chip, that you can actually create the capability of building a fault-tolerant system or an error-corrected system, then you have unlocked tremendous value. And that's how we look at it. So we look at it from one perspective on the amount of value we're creating by enabling very efficient chip scale scaling, right? The other way to think about it is to say, how much are you saving by not having to buy racks and racks of electronics? And for those of you who run labs or run companies, I think you know exactly what I mean when I talk about, buying yet another rack of equipment from, I don't know, Keysight or Zurich Instruments or Quantum Machines or whomever. I mean, these are, Orange or whatever. These are very, very expensive things to do. And if we wanted to think about scaling up to, let's just say 1,000 qubits or tens of thousands or even, millions of qubits, the cost of doing that and the energy required on an OpEx basis is enormous. And, the idea of incorporating that onto a chip transforms the ability to do it, and the delta between the marginal cost of a chip versus the marginal cost of a rack of room temperature electronics is enormous, and particularly as it relates to scaling. So I just want to say that from a business model perspective, you can think about trying to capture not only the ability, unlocking the ability to scale and get to fault tolerance, but also on a cost-saving basis, on a CapEx basis for the equipment you'd buy, and then on an OpEx basis for the energy you'd save. To be able to do that. And by doing that, it means that we've created tremendous value, which we should be able to capture from our prospective customers. And then the last thing I wanted to leave you with, and then Katie's going to join me on our Q&A, is just to talk about our roadmap. Not a lot of companies publish their roadmaps. We do. And so I mentioned that we release SEEQ-RED. SEEQ-RED is a reference quantum computer using room temperature electronics running on an analog basis, just the way you saw, Google or IBM's pictures in this presentation. We've gotten very good performance out of this platform, and we built it actually not to really run people's third-party applications so much, although we did, but as an internal reference point, because our industry doesn't really have very good benchmarks. And so what we thought was, let's us build our own reference system, our own benchmarking system, so that we could then, in our next 3 generations of computers, and the next one is coming out at the end of this year, so very, very soon, we could compare the performance of a chip-based system, or at least a hybrid chip based system, and then a fully chip-based system with this reference design. So by the end of this year, we will release a quantum computer that will have a quantum processor, single flux quantum XY control on a multi-chip module, a demux capability, multiplexing capability, so we'll see that, and you'll see gate level using control core, our software system. The following year, we will incorporate a Z driver, which will be, so that'll meet full X, Y, and Z control of a quantum computer, plus demux integration and digital readout. So that we'll have digital readout, digital control, full demux, fast active reset using our control core. And this will be the first 100% run chip-based quantum computer. And as we go forward from there, we'll begin to incorporate different aspects of error correction. So with that, thank you. And now I wanted to see if we can open it up to questions from Katie, or questions addressed to Katie and to me. And then we'll run our video, and then we'll be back again to talk a little bit more about how we fabricate our chips, because I didn't even really mention, we run a chip foundry. And so you're going to see actually how we make these chips and how we test them.
Thank you. This was really amazing and inspiring talk. Thank you for that, John. Also, David from the US says, thank you also for sharing the value proposition of SEEQ and your roadmap and ideas. This has been really inspiring. There are many questions that I will now share with both of you. And okay. I'm scrolling back through the Discord. The first question was asked right away by David from the US to you, John. Mr. Levy, how can you be a serial entrepreneur in many different tech areas?
So I've been working at this for a really, really long time in particular in deep tech, oftentimes on chip-based technologies. And so it's interesting, the process that we use, as you're going to hear, in building our SFQ chips are similar to the process we used when I was helping to run a MEMS company. So it's really taking the learnings of one and to another, A. B, having worked in the venture capital world where I've been on, I don't know, maybe 15 boards, something like that, technology company boards. I've worked with lots of teams. I've seen what works and what doesn't work. And again, it's really taking all of that learning, that real life experience, and applying it to, if you will, the next one.
Very valuable advice. The next is a technical question. Let me share that with you, Katie. Harsha from the US asks, what is a flux pulse and how is it different from microwave pulses?
Oh, good question. So that's really core to our in-house tech. So what we're trying to do at SEEQ is we're trying to control qubits using SFQ pulses. An SFQ pulse can be generated if you take a Josephson junction and then a loop of superconducting material, and you apply a magnetic flux through it. So when you apply magnetic flux through this loop, the junction has to change by 1 flux quantum, and then an SFQ pulse is emitted. This SFQ pulse has sort of like a quantized area. It's 2 millivolts per for a picosecond. And what we do is we capacitively couple these SFQ pulses to our chosen qubit. We're agnostic to the type of qubit as long as it's superconducting. Let's say a transmon. We'll capacitively couple this pulse to the transmon, send a series of pulse trains, and that means we can perform arbitrary rotations around the Bloch sphere using SFQ pulses. I hope that's a good whirlwind summary.
That is excellent. Thank you very much. Then, interesting question by Artem from Mexico. He asks, do you think Moore's law is applicable to quantum computing scaling? Who dares to comment on this?
Well, part of it's a complicated question because, in the previous talk, Danny was talking about the idea of reducing the size of qubits, that superconducting qubits are inherently large, although one can get into, how you can reduce the size of those. And our circuits, by the way, our SFQ circuits are really, really small. But we're at such an early stage in our industry, and there's so many different qubit technologies that I just think it's really hard to apply that kind of thinking to something where, it was really working in a mature design and manufacturing process around CMOS. And so you could make some reasonable predictions about that. I think we're too early to be able to make those kinds of estimates.
A quick question by Miguel from Mexico. You made some energy estimates. Are there current quantum computers from IBM, Google, D-Wave, where the energy efficiency was actually shown?
It's an interesting question, because I just saw a study, an internal study by a private consulting group, where they're trying to get that information, and we were looking at it, and it's not it's very, very difficult to do this. I'm going to just say that. And one of the things to think about is the difference between running things on a NISQ basis and running things on a fault tolerant basis. And you get very different profiles from an energy perspective. I'll just leave it at that. But it is so, it goes back to, again, these sort of the lack of standards and the early days of all this stuff. We don't really have standards, which is why we said to ourselves, let's build SEEQ-Red so that we at least have something to compare things to, and something that we think operates at a pretty high level, pretty efficient level.
Excellent. Then in the summer program, in the WOMANIUM Global Quantum Program so far, we had an introduction to neutral atom quantum computing, silicon-based, superconducting, photonic. Bacau from France asks, am I understanding that the plan is to be able to do this, what you presented from SEEQ, for most platforms of quantum computing? Or which qubit modalities can you target?
Okay, do you want to take that one first?
Yeah, I would say SFQ qubit driving is most transferable clearly to superconducting qubits. But within superconducting qubits, there's a whole ecosystem of different types of qubits one can study. So yeah, you could, this is transferable to transmon qubits, fluxoniums, so on and so forth. I'd say it's most easily transferable to superconducting qubit tech.
I would also add that we've done work with single nanowire, single photon detectors. And that we fabricated them, in our chip foundry. We did it maybe 10 years ago, and we built some of the fastest that have ever been built. And so we think that at some point we will incorporate those into our design, which would support these other. It's one of the technologies that would support these other modalities, but right now our focus, as Katie said, is really on superconducting. And it's really where, I mean, to be honest, it's where the largest companies and the biggest efforts are being made. I don't want to comment on whether or not that's going to be the dominant force in the dominant technology in the future. As I say, I think that it's going to be we're going to live in a multimodal quantum world, in which we're going to need to support multiple varieties of quantum technologies in a single platform.
Excellent. And Taha Ruaba from SEEQC had a similar question, also related to trapped ion and neutral atom quantum computing approaches. Do you expect that these approaches will die somewhere during the next decade because of scalability issues, while you work on scalability for other qubit modalities?
Katie, you want to do this one, or do you want me to do it?
I don't know. I think my outlook might be a bit bleak for the public audience.
I mean, look, okay. Let me tell you what I think. I think that just because something can function as a qubit and you can build a quantum computer out of it, doesn't mean that it's ultimately going to be the most scalable, cost-effective, performative quantum computer. However, that doesn't mean that those technologies aren't important. I think that they're critical. So I think, for example, we can imagine areas in which the long coherence time, but very slow gates of ion traps become useful for nodes on quantum networks. I think they could become useful for quantum memory. I think photonics could become very important for quantum networks. And so I think all of these things have to be built and explored, and we need to figure out what they're best at, and then incorporate them appropriately into a full quantum ecosystem. So I just because you can build something into a quantum computer, I would just argue, doesn't mean that's what will prevail in the future. But it's still important. But it's important to build it and to figure out where it fits.
Excellent, especially in this very nascent era still in quantum computing.
For sure.
Shika, there are many questions coming up. Shika Aldan asks, a question for you, John. Beyond showcasing the future potential of a quantum computer, what is driving industries now in investing in quantum computing?
Yeah, I mean, that's a really good question. I mean, and if you look at the work, I just recommend you to look at some of the work that BCG does for large companies about preparing these companies for a kind of quantum world. So if you're, why are we working with BASF and Merck? Because they know that being able to model molecules, for example, is core to their business. And if we think that one of the most useful and earliest applications of quantum computers could be quantum simulation, then they need to be looking at that now, and they are. But there's a kind of better analysis I refer you to, and they're publicly available studies by BCG and McKinsey and other groups.
Then everyone is very excited. How can we apply for jobs at SEEQ is a question. And what skills are you looking for?
More women.
Very good. And we have 45% women in the program right now. So that is very good. And then for everyone, what skills?
In technical roles.
Yeah, right now, SEEQ could really use more people like the early ENIAC engineers. People stood in front of very similar breakout boxes, stood wiring up devices, definitely test engineers. I'd say we're definitely keen for more.
I would say test engineers and process engineers in our chip foundry.
Great. I hear some complaints that the SEEQ website currently doesn't have available jobs, but maybe a cold application.
Yeah. Let's just say we're in a fundraising mode right now.
Yeah, great. And new times are coming up. Thank you very much. Let's move on to the virtual lab tour because there is much more to show from SEEQ, including the foundry. And then we will have Katie on for further Q&A about that. John, is there some advice that you would like to share with everyone present here, starting and continuing their quantum journeys?
I mean, look, I just want to say, I want to echo again what Danny said. This is, I mean, this is, I would argue, the most consequential technology of anything that we as humans are working on. I mean, maybe fusion technology might rival it, but it's so important in so many domains. And finding things that are consequential, that are meaningful, that you can apply your skills to is, for me, a privilege. And I think, and for everyone else, I think an extraordinary opportunity. So I just think that whether it's on the application side or on the chip side, design, testing, whatever technology you want, if it's research or whether it's applied the way we do, I think all of those are exciting opportunities.